Hi, I'm Eric Grossman, here to describe to you development of the Puget Sound Coastal Storm Modeling System, which is benefiting from a great team and federal, tribal, and local partners. The goal is to develop a standardized regional flood model to evaluate exposure to extreme storm and wave events with outputs at 1 meter along shore to inform assessments and priorities for coastal zone management, ecosystem recovery, and our fiduciary responsibilities to tribal communities. We are doing this by downscaling global climate models to resolve the influence of tides, storm surge, river discharges, and waves on coastal flooding and shoreline impacts, making use of 2.5 kilometer resolution weather reanalysis products, bias correction for winds over water, and the coupling of wave run-up models to a new computationally efficient 2D flood solver. Outputs are mapped and served on web tools to easily view physical and socioeconomic exposure. And this year we are coupling models of long-term bluff change and the influence of infiltration and groundwater, which is hugely important in the Pacific Northwest, with projections of significantly increasing intense rainfall in the coming decades. The model domain extends from the Columbia River north to above Vancouver Island with an unstructured grid for flow and includes the 24 largest rivers, including the Fraser. The model has a mean error of about 10 centimeters for water levels observed in NOAA and US gauges, and this allows us to resolve the influence of remote storm surge that propagates from the ocean into Puget Sound with a magnitude up to a half a meter or so. The model benefits from a new 1 meter DEM that we published last year and extensive work to get the salinity structure correct to capture the increase in mean water surface elevation that we observe into the deeper reaches of Puget Sound. The 2D flood solver Sphinx allows us to output flood extent, depth, duration, and overland flow velocities at 1 meter for current sea level and discrete increments projected in the future. With this workflow, we can also post-process results to define extreme event recurrence statistics cell by cell, like the 2 or the 10 or 50-year total water level, adding to what FEMA provides with the 1% annual chance flood. So far, we have results for about 15% of the domain, and partners are initially using the findings for port, transportation and water infrastructure planning, municipal and county climate adaptation planning, and with tribal partners, we're evaluating novel mitigation strategies that cultural and green solutions like clam gardens might provide for both food production and buffering the impacts to shores above. For the larger river systems, we're envisioning a compound flood model like we've developed for the Nooksack and Nisqually rivers using Delft 3D flexible mesh with the same boundary conditions and accounting for spatially varying land cover and friction effects. Our error is less than about a foot in the rivers and floodplains, and this 2020 Super Bowl flood shows the vulnerability of nationally important agricultural areas, salmon habitats, and proposed restoration actions to sea level rise as tides today are observed to backwater stream flow. We're really excited that model assessments of the proposed habitat restoration show potential to reduce flood stage by 2 feet today during these large events and up to nearly 1 foot under projected sea level rise and higher peaks stream floods through the year 2080. Perhaps buying time for communities to better plan for resilience and garner support for greener flood mitigation strategies today.